So in this video, we're going to be using the Rashford-Rice equation we derived in the last video to perform a flash calculation of a binary mixture of benzene and toluene. So we are given the flow rate of benzene is 4 moles per second and the flow rate of toluene is 6 moles per second entering our flash drum. So we can deduce that the total feed rate is going to be 10 moles per second. We are also given temperature and pressure, and we want to determine the flow rate of liquid and vapor going out of our tank and the composition of both liquid and vapor phases. Alright, so I'm going to code this out in our same notebook that we had for the last one, and let's begin. So first we want to set the temperature and the pressure. So our temperature is going to be 393 kelvins. And our pressure is going to be 150,000 pascals. We also know our total flow rate is going to be 10 moles per second. So we can call that total as 10. Then we can also define the mole fraction of each of our compounds in our feed. So we'll call that Z. And this needs to be an array because we have two components for our composition. We had 4 moles per second of benzene, so we can write that as 0.4, and 6 moles per second of toluene, so we can say 0.6. So we are actually able to compute the ratio of vapor phase to liquid phase for each component using the Ki value that we used previously in our last video. So if you remember, K was equal to the pure saturation vapor pressure, so that was P that T, and that was divided by the total pressure. So if you remember from our equation, we have a sum that is set equal to 0 with only one unknown. So we are actually able to use the root solver function to find our only unknown, which is V, the flow rate of vapor exiting our flash drum. Okay, so let's start off by making a function for our root solver. So we'll call this RR for Rashford-Rice and some vector in there. And then we need a variable to substitute in here for our vector. We'll use E, and that'll be 0. So for our return function, we just want to return our sum, which is going to need to be an array. And what the root solver is going to do is run through this summation equation and find a value for E so that it reaches 0. So I'll go ahead and type in our equation here. Okay, so since we only have one unknown that we want, it's going to be E. So if you remember from our equation, our summation equation from the last video, where that E was, there was a V over T, which is the flow rate of the vapor going out of our flash drum, and T was the flow rate going into our flash drum. So E is essentially going to be the mole fraction in the vapor phase. So we can define that to be for our root. Got our equation, and then we need to supply a guess. So because this is going to be a mole fraction, we want something between 0 and 1. So I'll just put 0.7 for now. and then we just want that one term, so we'll call it out just like that. And now we can use this information to solve all 4 of our unknowns. So let's do the flow rate of our vapor phase first, which we already have a v up here, so I'm going to use a different variable. I'll just say g. And so the flow rate of the vapor phase, if we think about how we can calculate that, we have our E value, which was the mole fraction in the vapor phase. So if we multiply our mole fraction by our total our total flow rate going into our drum, that should give us the flow rate of the vapor phase. Next, we can do for the liquid phase, and from our equations, that's just going to be our total minus the vapor phase. Whoa. Alright, and then let's see, for the mole fraction of the vapor phase, we will have our K value times X, but we need to define what X is going to be. X is going to be if you remember from our substitution equations from the previous video, we got xi alone. So that's going to be the equation we want to use for x, which is going to be z divided by our e times k minus 1 plus 1. Alright, and that should be good to go. And now we can see what those values come out to be. So if we want to see what these values are, let's see, we have G is our flow rate of the vapor phase exiting our flash drum. We have L as the flow rate of our liquid phase exiting the flash drum. We have X, which is our mole fraction of the components in the liquid phase. And we have Y, which is the mole fraction of the components in the vapor phase. So you can see here we have L is negative, which is impossible to have a negative flow rate. So that means that there's likely no liquid inside of our flash drum at all, and it's completely vapor at this specified temperature and pressure. But luckily, we used the same temperature and pressure in our plots up here when we calculated the dew pressure, dew temperature, and bubble pressure and bubble temperature. So we can actually see where on these plots our mixture lies. So we started out with 0.4 of benzene, which is this on the x-axis here. So if we look at 0.4 and we go up to our pressure of 150,000, we can see that it's falling underneath that red line, which was our dew pressure line. So that means that we're going to have all liquid, or all vapor, I'm sorry, because our pressure is too low for it to reach that dew point where that first bubble, or that first drop of liquid is going to form. We can also look over here at our constant temperature and see we have 0.4, we go up to 393, let's see, 393 at 0.4, yeah, that's going to be above our dew temperature also. So when we have a higher temperature, we're not going to be able to reach that first drop of liquid. So that confirms that we are all vapor in this scenario at this temperature and pressure that we're given with our mixture. So I also wanted to point out to you that this Rutherford-Rice equation doesn't work in every case scenario. Like we're seeing here, it's only going to tell us that we have all liquid or all vapor, because if it were a mixture of some liquid and some vapor, we would have a point that falls in between these curves on these plots here. So all of our numbers here are actually incorrect. If you think about it, if we have all vapor phase flowing out of our system, then we should have our G value equal to 10, which was our flow rate in. And the same with our mole fraction in the vapor phase. That should be 0.4 and 0.6. And there shouldn't be anything for our mole fraction in the liquid phase. This should be 0 for our liquid phase exiting. So hopefully you were able to learn something about the Radford-Rice equation and how it can be helpful, even if it doesn't tell you the correct information. It could still give you some kind of information about your mixture, like we did, where it told us that we had all of one kind of mixture of vapor in this case.